Welcome to the deep dive. Today we're tackling a really key piece for anyone serious about bow hunting performance. It's Dr. Ed Ashby's 2007 update, Part 1.
Yeah, and we're really zeroing in on the science behind arrow penetration.
Right, we know you want solid info, quickly but thoroughly, and this update, it's packed with that kind of deep analysis.
Absolutely. This isn't just opinion. We're digging into the actual research, the data, to figure out what really makes an arrow penetrate well.
So the core question, drawing straight from Ashby's work, is what are the actual drivers here? What determines how deep that arrow goes?
And our source is this detailed research update. So expect some real substance today.
Our mission, then, for this deep dive is pretty straightforward. We want to pull out the key principles from Ashby's findings on penetration.
And this is relevant whether you're, just starting out or you've been bow hunting for years. Understanding this can genuinely help optimize your setup, make better shots.
Exactly. Okay, let's get into it. Maybe starting with something Ashby felt was really important to clear up right away. This whole kinetic energy versus momentum debate.
Yeah, it's interesting. Even back in 2007, misunderstandings were already cropping up, specifically about how people were reading his earlier stuff, like Chart 4 from the 2005 update. It seems some folks were kind of pulling that chart out of context.
Right. So what was the issue? They were using it to say what exactly?
Well, the claim was that Chart 4 proved kinetic energy was basically the only thing that mattered for penetration, and that things like extreme front of center, or FOC, didn't really have an effect.
Okay, maybe quickly for listeners who aren't familiar, FOC, front of center. What's the quick definition?
Sure. It's just the percentage of the arrow's total weight that sits in the front half. So a higher FOC means the balance point is further forward.
And that affects stability and penetration, as we'll discuss.
Precisely. So people were looking at this chart, just the chart, and saying, see, kinetic energy lines up, FOC doesn't matter.
But Ashby pushes back on that interpretation.
Very strongly. He says, look, that chart had specific goals. First, it was just showing all the data gathered for extreme FOC arrows up to that point. Cumulative data.
Okay.
Second, it was giving some early signs that what he calls the heavy bone threshold still seemed to apply to these extreme FOC arrows.
And the heavy bone threshold, that's like the force needed to bust through a really tough bone.
Exactly that. You need a certain amount of oomph, basically, momentum, to overcome that resistance. And third, Chart 4 showed that their testing, well, it had kind of hit a wall.
The wall.
Yeah, what he called the measurable penetration limit. The extreme FOC arrows were penetrating so consistently deep with the impact forces they were using.
That they were running out of animal to measure penetration in?
Pretty much. It made it hard to see further differences between the extreme FOC arrows themselves. It showed they needed to test at lower impact forces to really differentiate performance more finely.
Okay, that context is critical.
It really is. And Ashby stresses Chart 4 was never meant as a direct comparison between extreme FOC and, say, normal FOC arrows with similar specs.
That comparison was somewhere else.
It was right there in the text accompanying the chart in the original update. The part, as Ashby puts it, that was often advantageously omitted by those making the kinetic energy only argument.
Ah, so you could only reach that conclusion by ignoring the direct comparisons provided in the same report. Classic case of taking data out of context.
Exactly, which
Right.
leads to why that context matters so much. Ashby brings up two key concepts that really affect penetration results: this penetration barrier and the measurable penetration limit we just touched on.
Okay, let's dig into the penetration barrier a bit more. What does that mean practically?
Okay, imagine an arrow hitting a big animal, like a buffalo. It travels through, maybe reaches the ribs on the far side.
Right.
If the arrow's lost too much of its momentum, its driving force by then, it just stops. It doesn't have enough push left to break through that offside bone.
So the offside rib literally acts as a barrier.
Yep. It stops the arrow, regardless of its initial kinetic energy. It's about the force remaining at that point.
Makes sense. Like hitting a wall you can't push through anymore, and the measurable penetration limit is just the physical depth available.
Basically, yes. On a big bull buffalo, Ashby says getting to those offside ribs takes about, say, 16 to 19 inches of penetration.
Okay.
But the maximum you can typically measure in a similar shot is only around 19 to 25 inches. After that, the arrow's either exited or hit the other side.
So even if an arrow could go further, you wouldn't see it in those tests because it ran out of medium.
Precisely. These physical limits can kind of mask the real differences between arrow setups, especially if both are performing well already.
Which is why those direct apples-to-apples comparisons Ashby mentioned are so important.
Exactly. He points back to the text that was ignored.
Okay.
He details 3 test series where everything was matched. Arrow dimensions, mass, impact force, kinetic energy, everything.
The only difference was?
The FOC. That was the single variable change between the groups in each series.
Okay, so what did those comparisons show? Let's start with the heavier arrows, set 1.
Right, the high-mass arrows. Even here, the extreme FOC group showed a 19% increase in penetration compared to the matched normal FOC group.
19%? That's not insignificant.
No, it's not. And Ashby notes the gain wasn't even bigger, mostly because the normal FOC arrows in that high-mass group were already penetrating pretty well themselves. They were often hitting those offside ribs, bumping up against that measurable limit.
So the ceiling effect was already kicking in for both groups to some extent.
Correct. And remember, when Ashby talks penetration, he means the depth of the actual wound channel created in the tissue.
Got it. Not just how far the shaft goes. He mentioned those numbers. 16, 19 inches to the offside ribs. 19, 25 inches max measurable depth. So the maximum possible difference they could even observe was capped. Maybe around 35% even with a pass-through.
Exactly right. That's why focusing on wound channel depth gives a more consistent metric, especially since pass-throughs on smaller game don't tell you the full potential.
Okay, so even with those constraints, 19% gain with extreme FOC on heavy arrows. What about the lighter arrows in Series 2 and 3?
No, this is where it gets really interesting. Even though these later extreme FOC arrows also hit the penetration barrier and the measurable limit,
They still did better.
significantly better, they outpenetrated their matched, equal kinetic energy normal FOC groups by 58% and 62%.
Whoa, 58 and 62%. That's huge.
It really is massive gains.
So wait, if kinetic energy was the only thing that mattered, and the KE was matched between the groups, how do you possibly explain a 60% difference in penetration?
You can't, really. It points very strongly to FOC having a major impact, completely contradicting that KE-only narrative.
Okay, that seems pretty clear-cut from those comparisons.
Now, let's circle back to chart 4 briefly. Ashby points out something else. The kinetic energy for the extreme FOC arrows in that chart. It was all in a pretty narrow band because they used the same bow. But the arrow mass varied quite a bit, which means their impact momentum, think of it as their pushing power, had a wider range.
Yet the penetration shown in that chart was super consistent, wasn't it?
Remarkably so. But Ashby emphasizes that consistency was not because of the narrow KE range. The real reason, it goes back to those physical limits we talked about.
The penetration barrier and the measurable depth limit.
Exactly. Let's break down why the penetration looks so uniform in chart 4. First, remember, it's only extreme FOC arrows.
Okay.
Second, get this, 92.3% of them reach the offside ribs. That's incredible consistency right there.
Wow, almost all of them.
And of those that reached the far ribs, 44% actually penetrated beyond the rib, and 25% of the total shots actually went past the maximum measurable penetration distance for those tests.
So they were maxing out the test conditions.
Pretty much. Out of 39 shots, only 3 failed to reach the offside ribs. The consistency was phenomenal.
So the numbers back that up.
Definitely. Ashby shows that if you exclude just the 4 lightest arrows, the ones that likely fell below that heavy bone threshold, the average penetration for the other 35 shots was 20.38 inches, and the standard deviation, just 0.825 inches. That's incredibly tight.
So because they were all hitting these physical ceilings, it looked like they were all performing identically, even if their underlying momentum might have varied more.
That's the key insight. The test setup at that specific impact force just couldn't show the full potential differences among the extreme FOC arrows because they kept hitting those limits.
Which is why he said they needed lower impact force tests later on.
Right. To spread the results out more and quantify the FOC effect more accurately across a wider range.
It really highlights how crucial it is to understand the testing context, not just grab a chart and run with it.
Absolutely. Now, there's another critical point Ashby makes, something else ignored by those misreading chart 4. The actual kinetic energy levels involved.
What about them?
Well, this is quite telling. He states that every single arrow in chart 4 had an impact kinetic energy significantly lower than the minimum recommended by KE proponents themselves for hunting buffalo.
Seriously, so even by their own standards, these arrows were supposedly underpowered in terms of KE?
Yet the extreme FOC ones were achieving that amazing, deep, consistent penetration we just discussed.
That seems like a major contradiction for the KE first argument.
It is. And Ashby adds that throughout the study, they consistently failed to find any reliable predictive link between impact kinetic energy and how deep an arrow actually penetrated tissue.
No correlation.
No predictive correlation. To drive this home, he presents data from the highest kinetic energy group they had tested.
Okay, tell us about this high KE group.
These were lighter arrows, averaging about 417 grains. They had decent designs, normal to high FOC, favorable shaft for rural setups. The shots were placed carefully back of shoulder, hitting only ribs, 20 yards, adult buffalo. So very comparable conditions to the Chart 4 shots.
And the results. High KE should mean great penetration, according to that theory, right?
You'd think so. Their average impact KE was substantial, 82.99 foot-pounds, some were up over 94 foot-pounds. Average momentum was .556 slug-sick.
Okay. And penetration?
Average penetration was only 12.20 inches.
12 inches? That's way less than the 20-plus inches the underpowered extreme FOC arrows were getting in Chart 4.
Way less. And here's the kicker. Only 15.4%, just 2 arrows out of 13 in that high KE group even reached the offside rib.
15%, that's poor.
It gets worse. Almost a third of them, 30.8%, failed to even penetrate the entrance rib cleanly.
Wow. So, let me get this straight. The extreme FOC arrows had less than half the kinetic energy.
46.3% of the KE, yes.
But achieved 67% more penetration.
That's what the data showed. So Ashby asks, point blank, did kinetic energy predict that? Does this maybe suggest extreme FOC has a real effect? The answer seems pretty obvious.
It's hard to argue with those numbers. KE clearly wasn't the deciding factor there.
Not at all. So if KE isn't the main driver, Ashby pivots to what is more important.
And he brings in another comparison, right? Using heavier arrows from a longbow.
Yes, another crucial comparison. These were shots on similar buffalo, same conditions, shot placement, angle, distance, broadheads, good arrow builds, normal to high FOC. The key difference was the arrows were much heavier, averaging 783 grains, shot from a longbow, so lower velocity.
Heavier, slower arrows. What was their penetration like compared to that high-speed, high KE group?
The average penetration for this heavy arrow longbow group was 13.92 inches.
13.9. Wait, that's more than the high KE group's 12.2 inches.
14.1% more penetration, actually.
Okay, that's surprising. What were the KE and momentum for these heavier arrows?
Much lower KE, as you'd expect. Only 35.32 foot-pounds, on average just 42.6% of the high KE group's energy.
And momentum.
Their average momentum was .496 slug at sec. That's actually 9.8% less momentum than the high KE group had.
Hold on. Less kinetic energy and slightly less momentum, but more penetration.
That's what the results showed. It really challenges the simple more energy equals more penetration idea.
So how does Ashby explain that? What's the physics?
He talks about stopping time. For a given impact force and resistance, a heavier object takes longer to stop.
Right, inertia.
Exactly. That longer stopping time means the force is applied for a longer duration. It's related to the concept of impulse, which we'll get to.
So again, Ashby asks the rhetorical questions. Did KE predict this outcome? Does this suggest arrow mass contributing to momentum, and how that force is applied over time is really important?
It certainly looks that way from the data, which leads him back to a core finding of the entire study.
Which is?
That in real tissues, the data consistently shows a positive correlation between impact momentum and penetration depth, assuming other factors are kept constant.
So more momentum generally means more penetration.
On average, yes. He says the increase in penetration is typically directly proportional to the increase in momentum for a given arrow setup.
And kinetic energy just doesn't show that same reliable link.
No. He states very clearly that KE has consistently failed to show that positive correlation in tissue tests and isn't a useful predictor of penetration.
Why not? What's the reason KE fell short in predicting penetration in something like animal tissue?
He gives a few key reasons. One, tissue resistance isn't linear. It increases disproportionately as the arrow speed goes up. Faster isn't always proportionally better against tissue.
Okay.
Two, it's about the mechanics of force, transfer over time, the impulse, which KE doesn't directly measure. And three, fundamentally, KE is energy, not force. Penetration is about applying force in a specific direction over time.
He also mentioned a decrement relationship for KE. What did that mean again? Not negative, but...
Right, not negative. It means you get diminishing returns. As you keep adding more kinetic energy, the rate at which penetration increases slows down. Each extra bit of KE buys you less and less additional penetration.
Okay, got it. So if KE isn't the key predictor, he keeps coming back to momentum and this impulse of force?
Yes, impulse is central. Assuming you have a good arrow flying straight, the penetration outcome depends mostly on the impulse of force delivered to the tissues.
And impulse is?
It's the total force transferred over the time of impact. You can think of it as net force multiplied by the time it acts. It's also equal to the change in the arrow's momentum. They even have the same units of measurement.
And he really hammered the point that energy and force are not the same thing.
Absolutely. Critical distinction. KE is energy of motion. Momentum is more like the directional force the arrow carries because of its motion and mass.
So momentum comes from KE and mass.
Right. Momentum is derived from a portion of the KE plus the arrow's mass. It represents the total potential directional force the arrow has right at impact. And since penetration is directional, momentum is highly relevant.
He used a bank account analogy to explain this, didn't he?
Yeah, and it's actually pretty helpful for visualizing it. Think of the KE you generate drawing the bow as money you earn. Some might be lost, but the usable KE gets deposited into your arrow's bank account. The arrow's mass is already sort of in the account. So mass plus usable KE equals your total bank balance.
And that bank balance is the arrow's momentum, its total potential force.
Exactly. That's the money you have available to spend at impact.
So what's spending in this analogy?
Spending is applying force to buy a work benefit. The main benefit we want is tissue penetration. That's a good purchase.
But you can spend momentum on other things too, things that aren't penetration.
Absolutely. Just like wasting money. You might spend momentum overcoming friction, dealing with a poorly designed broadhead or shaft connection, or losing force if the arrow deflects or breaks. Those are non-useful expenditures.
Okay, so where does impulsive force fit in?
Impulse is like how you spend the money. It's the average rate you spend your momentum balance and the total time you keep spending it.
Ah, so rate and duration.
Right. If the arrow stops inside, you spent your entire momentum balance. If it passes through, you had momentum leftover money still in the bank.
So to get deeper penetration, more work benefit, you need either a bigger starting balance
For momentum.
or you need to spend that balance more efficiently.
Exactly. Be more frugal with your force, which comes down to efficient arrow design.
And Ashby suggests focusing on efficiency has more potential.
Much more. You can only increase bow force so much, but making the arrow use its momentum, efficiently conserving it, applying it over a longer impulse time that multiplies the effect.
And the real-world data supports this focus on momentum and impulse.
Overwhelmingly, according to Ashby, the tissue tests consistently point to momentum and impulse as the reliable indicators, while KE doesn't hold up as well predictably.
It sounds like he was pretty definitive and maybe a bit weary of the ongoing KE debate even back then.
Yeah, he basically hoped that by laying out the physics and the analogy so clearly in this update, he wouldn't have to keep revisiting these fundamental distinctions in every report.
But he also cautioned that it's not just about momentum, right? There's more to terminal performance.
Oh, absolutely. He emphasizes that things like arrow flight quality and many other arrow design features are also crucial. The goal is to make the arrow, as he put it, stingy with its force. Use it wisely for penetration.
So momentum is foundational, but it's one part of a bigger picture the study was trying to map out.
Precisely. Identifying and quantifying all the factors that contribute.
Okay, so wrapping this up, the big takeaway from this deep dive into Ashby's 2007 update, part 1 seems pretty clear. In real-world hunting situations, momentum and the way that force is applied over time, the impulse, are much better indicators of penetration potential than kinetic energy alone.
And efficient arrow design is absolutely key to making the most of the momentum you have. It's about how effectively that force gets used.
We really hope this exploration has shed some light on these concepts for everyone listening, whether you're new to bow hunting or have been tweaking setups for years.
Yeah, hopefully it gives you some solid principles to think about.
Definitely something to consider regarding your own equipment, your arrow choices. Maybe this sparks some more thinking about arrow design, about FOC, and how it all ties together. Could be grounds for another deep dive down the road.
It's always a journey, isn't it? Trying to understand performance better, based on real data, always aiming for more effective and ethical hunting. That's the quest.